Take a piece of paper, cut it into half. Take one of the halves and cut it into half. Repeat this process over and over, halving the volume with every cut. How many cuts do you need before you can no longer go any smaller? Or is there no end to it? The discussion of what makes up matter is prevalent across ancient civilizations. What we know today as atomism, which is derived from the Greek word atomo, meaning indivisible. Atomism consists of multiple competing theories based on theology and philosophy, with little evidence and experimentation, which could not convince everyone. The most commonly known sides of the atomism debate came from ancient Greece, with Leucippus and Democritus in 5th century BCE proposing that matter consists of indivisible particles called atoms, while Aristotle before 330 BCE rejected atoms, instead stating that they are infinitely divisible. It was only another 2 millennia later was atomism embraced and refined by scientists, with atoms being the only method to explain discoveries in chemistry. In the early 1800s, John Dalton proposed that each element comprises of atoms of a single unique type, which cannot be altered or destroyed by chemical means, but can be combined to form more complex structures, what is known today as chemical compounds. Dalton's proposals were concluded from experimentation and examination of chemical proportions of tin oxides, making it the first scientific theory of the atom. In 1897, J. Thomson discovered the electron through his work on cathode rays. Cathode rays are fired through a Crookes tube in a vacuum. When they pass through an electric field, the cathode rays are deflected, leading Thomson to conclude that the cathode rays are composed of very light negatively charged particles he called corpuscles. By measuring the mass to charge ratio, he discovered that corpuscles are 1/1800th the size of a hydrogen atom. This led to Thomson suggesting that atoms are divisible, with corpuscles being their building block. He proposed the plum pudding model of atoms, corpuscles being the plums embedded in the sea of positive charges, the pudding, making the overall atom neutrally charged. The plum pudding model was disproved in 1909 by Thomson's student, Ernest Rutherford. Rutherford's colleagues Hans Geiger and Ernest Marsden conducted the Geiger-Marsden experiment, where alpha particles are shot at thin sheets of metal. Based on Thomson's plum pudding model, where the electrons are small and positive charges are sparsely distributed, it was hypothesized that the alpha particles would pass through the metal foil with little to no deflection. Rather, a small fraction of alpha particles experience heavy deflection, leading Rutherford to conclude that the positive charge is concentrated in a very tiny volume to produce an electric field capable of deflecting the alpha particles. Rutherford subsequently proposed a planetary model, where a cloud of electrons surround a small compact nucleus of positive charge. The planetary model was updated in 1913 by Niels Bohr, who proposed a model that the electrons of an atom orbit the nucleus, but could only do so in a finite number of orbits. Later in 1913, Henry Moseley provided additional evidence supporting Niels Bohr's theory, which also refined Ernest Rutherford's and Antonius von den Broek's model, which proposed that an atom's nucleus contains a number of positive charge equal to that of its atomic number. In the same year, radiochemist Frederick Soddy experimented with products of radioactive decay and discovered that radioactive elements contain more than one type of atom with the same chemical properties but different atomic mass. Margaret Todd suggested naming them isotopes. J. Thomson also conducted an experiment by channeling a stream of neon ions through magnetic and electric fields, where he observed two glowing patches on a photographic plate the ions would strike. This suggested that there were two different deflection trajectories, leading him to conclude that the ions have different mass. It was only until some 2 decades later was the nature of isotopes explained by neutrons, which was discovered in 1932 by James Chadwick. The neutron was first discovered in 1928 by Walter Bohr, albeit with a mistaken identity. Upon bombarding beryllium with alpha particles, he observed the liberation of highly penetrating electrically neutral radiation, which he thought to be gamma radiation. James Chadwick, however, disagreed as the ionization effect was too strong to be caused by electromagnetic radiation with energy and momentum conserved. In 1932, he subjected elements to the mysterious radiation and measured the energies of the recoiling charged particles. From the measured energies, he deduced that the radiation comprises of electrically neutral particles of a similar mass to the proton, rather than the massless gamma radiation. The particle is the neutron.